Let's start our lecture today. So before we start, I would like to tell you that this could be the last lecture that we are going to discuss by today. So after the class today is the next class onward, we are going to focus on the passive question only. Okay. So so there's nothing much. So this one will be the last class lecture, I would say. So the remaining one we'll be discussing about all on the passive question. Okay, so we go to the last part. Start recording. Okay, so today we are going to talk about the MOSFET. So whenever we talk about the MOSFET, we will know that it's related to the transistor. But how does the MOSFET related to the, let's say, semiconductor? For example, like the NMOS or PMOS, whatever that you learned in your practical lab. So all are using a MOSFET. But what is that about? This is the discussion that we are going to focus on today. So let's see. So normally MOSFET, what is a MOSFET? MOSFET stands for metal oxide semiconductor field effect transistor. MOSFET, MOSFET. Why does it say so? So imagine that this is your circuit. Okay, your transistor is somewhere around here. Imagine this is transistor. Okay, but how does the transistor looks like in the semiconductor aspect? So normally, when we are talking about a transistor, you will be having the layer of the metal. Then after that, you'll be having a layer of the oxide. Then you'll be having another layer of your semiconductor. It's either a P-type or the N-type. Then you only connect to the battery or power supply. Okay, MOS. So that's why we call it MOSFET. So it's one of the two major type of transistor. So it's used extensively in the many digital circuit because it's more size. It can use on the million of the devices or million of the transistor can be fabricated into one single circuit. Just like what your assignment is doing. Okay. So last time when we are doing the lab, maybe we are dealing with, let's say, inverter. So when we are dealing with one inverter, maybe we have one of the PMOS, another one is NMOS. Okay, then one input, one output. Then when we are dealing with the, let's say, NAND gate. Okay, when we are dealing with the NAND gate, we need to deal with the two PMOS and two NMOS. This is what we are learning. But in your assignment, you are going to deal with the integrated circuit. Okay, something like this. Okay, you are integrating first circuit and the second circuit. So in the fabrication, they are basically creating a very, very tiny circuit. For example, this one is most simple one, only two components into one single. Let's say this one is a wafer, maybe it's just a little small part around here only. So it will contain these two things. Okay, so we have two things. One is the N-channel MOSFET, another one is the P-channel MOSFET. Okay, so all these circuit we will call it as a complementary Mos circuit. That's why we call it as a CMOS. Okay, let's go to the picture wise and see what will happen. So this one is a MOSFET. It's capable of the voltage gain. So whenever when you have the two plate together, you will have the voltage gain. Okay, and signal power gain. Just imagine this is the metal that I mentioned just now. You have an insulator, or we so called as an oxide layer. And this one is either the N-type or the P-type substrate. Okay, but how does it look like? So let's see what happens if you connect in the, let's say, reverse bias or the forward bias. What will happen? So normally when we are going to have a parallel layer, okay, as long as there's a positive and the negative, they will be having the capacitance. This one we learned before. Okay, but what happened in the MOS capacitor? So imagine you have something like this. Imagine if you have something like, okay, this one is the metal layer outside. So this one is the P type. Then you connect to the negative. Another one connect to the positive. So if you connect this way, negative electron will be gathered around here. But the positive charge will come into here. Okay. So whenever when you see the positive and the negative, in between this, there will be the layer of the capacitance. But you might be wondering, what happens if I connect in the reverse way? So let's say if I draw it again, positive, negative, positive, negative. What happened if in this case? So let's see. If in this case, imagine that originally all the positive charge coming to here, positive charge coming to here. Okay. And then if you have a positive charge inside here, it will forcefully induce the region. Let's come back to here. Okay, originally, if you connect this way, you will induce a region with all the positive charge, all the whole are here accumulated here. But imagine, originally here with the positive charge, but when you have the positive charge coming in here, it will forcefully induce a area in somewhere around here. Okay, this will be the induced region. Okay, let's see what I said. Get back to the slide. Okay, see, a MOS capacitor with the P type subtract. The top metal is the negative voltage, then the bottom one is the positive voltage. So from the parallel capacitor, we can see the negative charge will be acid on the top. This one makes sense. And then if the electric field will penetrate into the SC, so the major carrier hole will experience a force towards the oxide, which means that if you have a negative charge here, so positive charge will come here. This will induce a force over here. Okay. Then this will be accumulating the layer of the hole on the oxide region, which means that originally all the positives are somewhere around here. So right now it will gather in this area. But the other way around, if you are connecting in the reverse way, positive charge here, okay? So it will forcefully induce the area in here, okay? Because it will push all the positive charge in one more area here. Okay, whenever when we are talking about all this diagram, we will be saying that, okay, the energy band diagram will be having the energy band changes also. How are we going to see these two diagrams? This two diagram is basically talking about the energy. Last time when we are dealing with all the conduction band energy and let's say valence band energy, and in this case, whenever when we talk about the p type and the n type, p type here and n type here, okay, it will also having the conduction band energy. But how does the conduction band energy looks like? So imagine if we had this, maybe I crop this picture, set this. Okay, maybe I arrange in this way. It will look slightly better. Okay, this one rotate, right? Okay, this one still Okay, let's do it this way. So we have this, and then this one is the rotate 90 degree. Oh, sorry. This one is a, oh, what happened? So this one is rotate left 90 degree. Ah, okay. So basically this thing will look something like this. Okay, enlarge bigger. Okay, you assume there is a live one, something like this. Okay, so this one metal is somewhere around here. This oxide area is somewhere around here. Then this region will be this region onward. Okay, this region will be this region. Something happened here, but you can see that right now this one will be slightly different. So let's see what are the differences. Let's get back to the slide. Okay, imagine this one is a picture. Okay. Yeah, alamak, malas saya webcam. Okay, start in 10. So this one is connected in the negative voltage, which means that when you're connecting this to this will be a negative. This one connect to the positive area. Okay, connect something like this. So when you connect this into the negative, if this is the P type, then the conduction band energy will be curved like this, down curve, and down curve. Okay, and then this area will be accumulating the positive charge, positive pole. So basically this one, let me redraw this. I remove all this. So basically this one is to connect to the negative. So this one is a metal. Okay. Remember just now when we discussed if all the electron here, all the electron will gather in this here, all the positive will come into here, and you will gather in this region. So for the graphites, metal, oh, oxide, and this one is the. So in this graph, it will look something like this. Down curve, EC, EF, EF, EV. One should be the EF5. Okay, above one is the EF5. Okay, the curve here, somewhere around the point. This region will be the accumulating of the positive charge, which is about this region. Okay, if this is connected to the negative charge. Okay, so this is how it looks. The other way around, if we connect it to the positive charge, positive, this one. Okay, and then we can try to redraw it again. So right now, here are full with the positive charge. And then let's see how does it looks like. A view, curve in the above. Something like this. EC, EF, E, EV. Okay, then C, EFI, EF, EV. And then right now, you can see that in the curve area, this will be the induced region that I mentioned just now. In this region forcefully create a additional area here just to accommodate all the positive charge. Okay, in this case, these two are the p-type semiconductor. Okay, at this point, can you understand? Okay, I count to 5. In no question, then I can proceed to the next. 5, 4, 3, 2, and 1. Okay, so the energy band diagram of the MOS capacitor with a p-type substrate from a large positive gate bias. What does it represent? Okay, back to this. If we are just supplying the moderate voltage, for example, let's say if just supply maybe a 5 volt, it will induce the area. The area we will denote it as a SD. But let's say if we are going to supply, let's say 100 watt, okay, it will induce more area. This area we call it as a SDT. Okay, just a denotation. Okay, and then this will be the inversion of the layer of the electron. Then by supplying the sufficiently large positive, then the gate voltage has been inverted from the p-type to the n-type. Okay, sorry for the little mistake just now. This should be the negative area. Negative. Okay, this should be the induced negative. So if we are going to supply big enough, the induced area will become bigger and bigger. Imagine, let's say 5 volt will be something like this only. But if supply 100 volt, it will become like this. So here we'll accumulate many negative electrons. So eventually, when you're supplying more and more, originally this one is a p-type. But with the more and more electron, this will become the n-type. So let's say if you supply, let's say 1000 watt, okay, sooner or later, the whole area will become the negative electron. Okay, then this will become the n-type semiconductor, no longer a p-type. Okay, because originally positive charge coming from here, negative charge coming from here. Okay, negative charge will induce here. Okay, we will accumulate here. All the negative charge will come into here. But you need a region to accommodate everything because this one is originally a p-type. So all the p-type, it will create the region for it to put all the negative electron here. Okay, so this is how the concept works like. Okay, we were saying that this will be the inversion layer of the electron. This area will be an inversion layer of the electron over here. So let me have a drink of water first. Okay, so we're also doing the same thing with the n-type semiconductor. Just now we are dealing with the p-type. So right now is an n-type. So metal oxide layer, and then this one. So positive charge coming to here. Here full with the positive charge. This one is an n-type. So most of the electron will be attracted to here. Okay, same thing. But if you connect in the reverse way, right now, here all become the negative. Okay, become negative. Okay, when you become a negative, positive coming to here, right? When you positive coming to here, originally this one is the n-type. So here it will create the region to accommodate all the positive charge here. Okay. So if you are providing 5 volt, maybe it become like this. Let's say you're providing 100 volt, then the area can be bigger, positive charge. If let's say by 1000 ohm, eventually this will become p-type, no longer n-type. Okay, at this point, any question? Okay, I count 5 times. 5, 4, 3, 2, and 1. Okay, so let's go to the next slide. It will still be a conductive semiconductor. Okay, why are we going to use semiconductor? Because sometimes we want it to be non-conductive, sometimes we need to be conductive. That's why we need to use a semiconductor. Okay, okay. So let's see this. Okay, one of my slide here. Okay, so same thing happened. Right now we are dealing with all the n-type. So if this is an n-type, connect to positive, this one connect negative, connect large negative. This is a moderate negative. Okay, if connect to the positive, the cable will look something like this. Here will be accumulating all the electron because electron coming to here. So all full with the electron. So that's why the electron is somewhere around here. But if you connect to the reverse way, and then originally this was an n-type, but all the positive charge will be coming to here. So it will induce a positive space charge region, SD. If you are connected to a large voltage, so we'll be having the larger area. Okay, so here will be an inversion layer of the holes. So if you are large enough, then your n-type become p-type. Okay, so right now, let's deal with the formula. Just now we're dealing with the theory part. Right now, we are talking about the formula part. Okay, what are the formula of the yeah? We can say the old one. Oh, okay, remember. Okay, last time we learned about this built-in potential barrier. On Na and D over Ni squared. This thing is from the PN junction. Last few weeks we learned about this. We do a lot of the exercise on this. Okay. What happened? Since we are going to have a p-type semiconductor in this case, can we calculate the potential voltage also in this case? Okay. One thing you have to know that in order for us to calculate the potential voltage, okay, we will name this as a potential. And this potential difference will be the difference between the intrinsic Fermi energy level and the Fermi energy level. Intrinsic Fermi energy level is the absolute Fermi energy level if the temperature is 0. But this one, if there's something mixed inside here. So there's the difference. So the difference between this, we will denote it as this one, this symbol. But how are we going to calculate this? In order for us to calculate this marks the difference between the EFI and the EF in this curve. And then this thing will be equals to the VT ln NA NI. So compare back to the thing. Compare back to the built-in barrier. You can see that actually both formula are quite similar, except it don't have the ND other and I only one. It take out one part. Why? Because this is only the p-type semiconductor in this case. We are going to deal with the p-type MOSFET. Okay, so this thing will be much simpler. All we need to do is to know the Na, know the Ni, then we can find the potential difference between the EFI and the EF in the MOSFET of the semiconductor. But I don't want to waste a lot of time in dealing with this because I think many of us already quite familiar with all these things. Okay, so let's go to the next part. And we also need to deal with the space charge width. What are the space charge width? Space charge width means that this area, if we are going to supply a very high voltage here, it will induce a positive space charge region. And it will be written in this way. This formula. This SD is the region here. This one SD. And then this will be equals to the 2 epsilon S. This thing is the potential difference. E and A. You can see that basically this formula is quite close to the formula that we learned last time. Okay, just that you need to do one NA only. Okay, you don't need to do the ND. And this will be quite similar to the one-sided PN junction, which means that when you have only the NA, ND is very small. You can compare this thing with this W. Basically, everything is almost the same, except VBR and VR, it will replace with this thing, epsilon S. Okay. So the threshold inversion point for the p-type. Okay. There is also the maximum space charge. Okay. We can use this to calculate, but eventually it will reach the saturation state. What are the maximum space charge region? Which means that when you are trying to induce this thing, trying to induce this, what are the maximum SDT? To calculate the maximum SDT, all you have to do is to replace the 2 with the 4 only. Okay. Then this thing, you calculate through the formula just now. VT, ln, and A over Ni. This one. So you can see that basically this one actually is kind of direct. So maybe we try one example here. Imagine. Wait, let me see. So imagine if we have an NA equals to, let's say, 2 times 10 to the power 15 cm minus cube. Then your, let's say, T equals to 300 K. This one is a silicon. At first, all you have to do is to calculate the potential difference. FP. And then second thing is to calculate the SDT, the maximum state charge rate. SDT. Okay, let's try this. Okay, what's the answer for the potential and the width? Brenda, are you here, Brenda? What's the answer for this? 0.3056 volt. Any plus one answer? The rest of you? Okay, fair enough. So SDT, your answer is 6.2892 times 10 to the power negative 5 cm. Plus one? Any? Or you get a different answer? Lao Lục Jing, what do you get? Okay. Hu Heng Dong, what do you get? Okay. So basically, this is how we do the calculation. So let's say if this one is the n-type substrate, okay? So if we are dealing with the n-type, just now when we're dealing with p-type, we use this formula, Fp, Vt, ln, and AO, where Ni. When we are dealing with the n-type, we just need to change the Na to Nd only. Then same thing, maximum width, it will also refer to this. This one put to here, Nd put to here, then we can calculate everything that we want. Okay, so let's try this example. Okay, so this is the p-type, obviously, and A. So calculate the, okay, normally we need to calculate two things. One is the F, this one delta F, another one is the SDT. Try to calculate these two items for this case. Okay, in this case, what are the answers? Let me pick someone to answer this. Chua Yu Yang, what are the answers for these two items in this slide? Chua Yu Yang, are you here, Chua Yu Yang? 0.3473 watt, 2.99 times 10 to the power 5 cm. Okay, any plus one for this case? Okay, very direct and simple. Okay, so let's do this. Okay, I will this. See this slide. What are the work function difference? So basically, in the semiconductor, MOSFET semiconductor, we have the three kind of the items inside here. First is the metal. Second one is the insulator, which is silicon dioxide. Third type is the P type. Okay, these three items. Okay, so in these three items, all these three items will be having their different energy level. For example, in the metal, the Fermi energy level we write as a EFM. Okay, but in the, let's say, silicon oxide basically is an insulator. So that's why the conduction band energy and the valence band energy is having a very, very big gap. This thing we last time we learned before. Then the energy gap is roughly around 9 eV, standard one. Okay. And then this one is the beta semiconductor. Beta semiconductor we used to deal with before. We have a EC, EFI, Fermi energy level, then the valence band energy level. But we convert these three items into the vacuum level. Okay, vacuum level I think you all know lah, which means there's nothing there. What is the minimum level of the vacuum level? So the difference between the Fermi energy level of the metal with the vacuum level, we write as this thing, delta M. Then the difference between the vacuum level and the conduction band energy level for the insulator, we will write as a ESI. And then for this semiconductor, the gap, we write ES. But if we are trying to combine these three things together, what will be the energy level looks like? So this thing will be a little bit complicated. So you don't have to remember everything. You just need to roughly know only. Okay. So imagine this is a vacuum level. Okay, it will increase like this, increase in this way, and then this is the coming from here, this one, from the metal. And then when you are joining these three items together, the insulator, it will increase in this way. This one is the EC of the conduction band, which is this one, this thing. But it will increase theoretically. Don't ask me why it will increase. Yes, it will increase, but I cannot answer why. Okay, scientists say it will increase. Okay, so it increases in this way. So originally, compared to here and here, okay, before increasing, it will be something like this, delta M. But after increase, this will be a ESI, which is somewhere around here. This is somewhere around here. So it will increase like this. Then you have a EC, EFI, then EF. Fermi energy level right now is standardized everything. Okay, it's standardized the Fermi energy level, then conduction band energy level. Then from here to here right now. Originally, EC, okay, is the gap between here and here. So you will take the EC somewhere around here, here and here. This thing will become this. I know it sounds like a little bit complicated, so let me show you again. Okay, so let me highlight this. So this one, oh, not transparent. No. Okay, never mind. Yeah, cannot be transparent. Okay, never mind. I try to draw in this way. Okay, this one will be come in this part. Okay, and then this is the vacuum level. Vacuum. Then this one will be this one, somewhere around here. And then this one, yes, will be this one. You can see that this thing, the yes here, this one yes and yes, is before it get increased. It will be the gap between here and here, which is this one. Okay, right now you compare this way. This yes, adding with this, will become this. Compared to the right hand side, this one will become this one, which is this one. This way here. This one. And also this one. This and this adding up together will become this. Okay. So the remaining one, the vacuum level will increase, it will increase, and then this vacuum level it will push up a bit because it assumes the vacuum level is already starting to changing here to here. Okay, so it will write this one in here because it assumes the vacuum level is getting to the highest level. Okay, the thing we need to know is how to calculate this thing. So this one, EVOSO. This gap is the vacuum level gap before and after the joining. Okay? And then this one, EC and the EFI is about EG divided by 2, roughly. For me, energy level, it will maintain in the same thing than the conduction band energy. At this point, can you understand? Okay, this part. Okay, I count to 5, 4, 3, 2, and 1. Okay, let's continue. Let's see what are we going to do with all these things. Okay, here. So we sum all the energies from the Fermi energy level on the metal side to the Fermi energy level on the semiconductor side. So basically, what he have to do is to sum the energy level, all this gap will be equal to all the gap over here. Okay, what he mentioned is something like this. Sorry. Yeah, this one. Okay, so let's see. You want to do something like this. This one is this one. Then this one will become is this one. This thing plus this thing, these two add together will be the yes, this thing, this one, uh, add this one, add this one, add this one, yes so, yes so, and then add this one, delta P. Okay, so basically what he do is by adding these two things together, it will become adding these four things together. Okay, so formula wise, he basically just rearrange everything. It will become like this. At first, he remove all the E, I think. Okay, remove all the E. This one all divided by E, divided by E, divided, 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 divided. Then he tries to rearrange this. It will become this ultimate formula. So eventually, it adding these two together will become this potential. This potential, it was saying that this is the metal and the semiconductor work function difference, which is the difference between the metal and the semiconductor. What are the voltage difference between the metal and the semiconductor? So by having all this information, basically you can calculate the difference between the metal and the semiconductor. Okay, but how are we going to use this? So same thing also, if we connect to the N type or connect to the P type, it will also have the different response. Okay, just now, P type, when you are trying to connect to the positive energy, sorry, excuse me. Okay, wait, let me use my pen, start inking. So this is the M plus. M plus means that you are trying to supplying the negative here, negative coming to here. P plus, so providing the positive here. So if you are connecting to the M plus or the P plus, it will be having the different formula also. Okay, but the only difference is the negative value over here only. Okay, you can see that here for the M plus, it will become like this, Eg 2E plus Fp. Okay, this one is Fp also, but the negative is slightly different. There's a minor difference. Okay, so let me close this. So maybe I try one example so that you can familiar with this. Imagine this. For the aluminum silicon dioxide. So let me write in this way. So this one, 3.20 V S 3.25 V Eg 1/12 eV and A 1 times 10 to the power 15 CMS cube. Okay, you want to determine the UMS. Okay, we want to find this. But how are we going to find this? So at first we need to identify the right formula. Okay, so in this case, it didn't state anything clearly. Okay, this is the, but we can know that this one is a P type. Okay, P type doping at the Na. So if the P type doping at the Na, basically we can either use this or this formula only. Okay, so we have two formula to choose. So this one is the Ms will be equals to negative Eg over 2E plus Fp, or Eg 2E minus Fp. But how are we going to find this? this thing we have already learned just now. This will be equals to KT over E ln NA over NI. Okay, so at first you find the FP, and then this thing, all you need to replace inside here, EG we know, divided by 2E, then we can find the answer that we want. So you can find either the M plus or the P plus also, no problem at this case. Okay, so try to find this. Try to find this one, delta FP, then try to find this and this for the M plus and the P plus. Okay, what are the answer of this one? The potential. 同学们 okay, potential he get is 0.2877. Okay, so what are the M plus and the P plus for this delta MS? 0.8477, then minus 0.8477. Any plus one? Okay, good. The rest of you? Do you get the same answer? Lim Wan Yang, do you get the same answer? Are you here? Low Tonian, do you get the same answer? Hello, can you hear me? You get 0.2723 for the P plus. This one you get 0.2723. Okay. How many of you get this for the P plus? But what about the, let's say the potential? Low Tonian, do you get a 2.2877? 0.2877. Same potential. So all you have to do is to use the EG over 2E, then minus this thing only. Okay. 1.12 divided by 2. What are the value? Calculator. 1.12 divided by 2. 0.56 divided by 0.2723. 0.2877. Mm-mm. Okay, where are 2723, right? The answer should be 0.2723. 0.56 deducted by 0.2877. 0.2723. Okay, function one. I think you need to check the answer again. Okay, whatever I did just now is when you are trying to connect to the P plus and the M plus. But what if this case is not in the P plus and the M plus? Okay, so when the case is not in the P plus or the M plus, okay, let me remove all everything here. So originally this formula looks something like this. Ms will be equals to the minus plus Eg over 2E plus delta Fp. Okay, but if this one is the P type for the M plus polysilicon, M plus silicon, Ms will be equals to the negative Eg E plus delta Fp. Okay, this one is a P plus polysilicon gate. Ms will be equals to the Eg over 2E minus delta Fp. But in some cases, for example, just now what we did is the P plus or the M plus. In some cases, it didn't state it's the M plus or P plus or not, but it gives you this one, delta M. Just like this case, okay, it gives you 3.2. So in this case, if it didn't mention anything, you should use the 3.2, deduct all this answer. Okay, this is how we did it. Okay, so in this case, for example, if we make it general, okay, we don't care it's an M plus or P plus, we need to calculate the delta MS. Then we need to use this formula. This one. Yeah. Delta M minus plus Eg over 2E plus Fp. So if they didn't state any M plus or B plus, but it gives you some information like this, then all you need to do is to put in the value inside there only. 3.2 minus, let's say, 3.25 plus 1.12 divided by 2 plus the delta Fv, 0.2877. Okay, to get the final answer. Okay, so in this case is 3.2 minus 3.25, then minus 0.2877, then minus 1.1, sorry, 0.2 divided by 2. So you will get negative 0.8977. It's more or less like the answer that you showed just now. Okay? One of you calculated 0.8977, right? Just now. 477. It's quite close to it. So basically, we have three formula. One is, it didn't mention whether it's a p dot or the n plus or the p plus. So the difference will be minus plus Eg over 2 plus delta Fp. But if it's, let's say it's the n plus or the p plus, then you need to use another formula, which is this and this. Okay, this is n plus negative Eg plus O2E plus delta Fp. So this is a Eg over 2E minus delta Fp. Okay, this is the case. So basically, if this is a n-type semiconductor, generally still the same, just that you need to use the minus pressure only. Okay, so I think this will be the lecture content for today. So right now, let's move to let's see the past year question. Go to Google Classroom. Sorry. This one. Go to this one. I have uploaded the material. Try to do the question 1 and question 2. Okay? Try to do the question 1 and the question 2 of this past year question. Then we will discuss the answer later. You can start doing it now. Okay, by the way, I think today maybe we couldn't discuss the answer for the past year question. So I think you guys just do it, take time to do it, then we only discuss by the upcoming lecture class, which is this Friday. So some of you may need to prepare your presentation for this week, and good luck to you. And if you don't have any question, you may leave the classroom now. Thank you very much for your time and have a nice day. Thank you, everyone. Okay, bye, everyone.